Right, so it's 10. Uh, yeah, and by 10 I mean like 10 p.m. So, this is very late night, and I'm making this video. What's going on, first of all? Why did I post a lot of material in this last week? I was figuring out some stuff. So, first of all, recently I was having kind of an identity crisis, basically, because I mean, it's that pressure of having a goal and working towards that was just suddenly lost for me. I mean, I thought this would make me feel better, but then for some reason, it's making me feel worse. So at the very first day when I completed my JEE advanced stuff, so I mean, I thought I'm free and I can do whatever I want. It turns out that actually I'm not. I mean, physically I was. My schedule was much more freed up. Mentally, somewhere I'm not free. And yeah, I mean, like that kind of freedom that you can do whatever you want to. You can code for a whole day. You can learn guitar or something like that, right? Yeah, starting from the basics, even when you know nothing about it, you have zero experience. That thing somehow I've lost it, right? So I have to get it back somehow, right? I have to get it back. And also I was fearing that maybe my skills are deteriorating because I didn't yeah, I mean, like, I didn't actually do any calculations in this whole week. So it was a kind of uneasy feeling because I'm not used to that. I'm used to doing like thousands of calculations each day, which means this was unusual, and I was just like playing video games throughout the day. And I thought that everything will get better. I mean, I'll be more relaxed. I was more relaxed, but also it was more mundane. Yeah. So the conclusion is uh, that less stress is probably not what you should have for more happiness. It's like you should have stress, but then you should also have sense of achievement over that stress. Anyway, why am I talking philosophy? I'm here to solve this center of mass thing. So we did till actually we completed center of mass completely, and now we have the collision stuff, right? Yeah. Okay. It's still really weird that because it's 10 at night and still I'm so energetic. It's just weird. Something clicked in my brain and now I'm here. Yeah, let's just get this over. Okay, so where was I? This 4. Well, we did that, right? Yeah, we did this as well. Okay, where is it? Oh, come on, there's only illustrations. Okay, that's 5. Linear momentum, we know that. Okay, I think it's just. Okay, what's this thing? System of variable mass rocket propulsion. No, not interested. You already know the rocket equation and everything. Okay, just keep on going. What's this thing? Oh yeah, so injection system. Wait, I think we did that, right? Oh, okay, 8 and 9. 8 and 9 are what are remaining. Or was this on collision or what? This was rocket propulsion. Okay. Well, I think this we did. So then we just have collision now. Alright. So now we'll explain some formulae when I'll solve questions. So for now, we're not doing anything. Okay. Impulse of bodies. Yeah, maybe I know that. Loss of kinetic energy in collision. Okay, keep on going. Oblique collision. Right, there's like a lot of cases for this. Oh, this thing is actually very, yeah, I mean, it's very beautiful because what actually happens is that the, yeah, it bounces off and it bounces off elastically. It's as if it was continuing, but then it's mirror. You will see that when I will solve the problem. Okay, just keep on going. Okay, injector exercise 8, let's go. First question. Particle mass m moving velocity v collides around elastically with another identical mass of mass at rest. The velocity of the first particle just before collision is. This guy's mass m, its velocity v, another mass, identical mass. Okay, fine. So the thing is, for elastic collisions, if you have mass m1, m2, and this one is like moving with speed u1, this is moving with speed. Okay, that don't. Okay, this is moving with u1. This is moving with u2. Um, then the momentum that's imparted on our M2 guy, that is equal to, it's just 2 M1 M2 upon M1 plus M2. This is the harmonic mean, right? Because yeah, just divide by that, you get 2 upon 1 upon M1 plus 1 upon M2. That's our harmonic mean. But that times the relative velocity, which is just U2 minus U1. Yeah, I mean, if I remember correctly, that was the thing. Okay, cool. So in this particular case, our U1 is, what is this once again? V, and U2, oh, it should be probably U1 minus U2, sorry. Because this has to be going faster than that. Okay, yes, like U1 minus U2. So now U1 is V and U2 is 0. So this just becomes what? 2 M1, M2, both are the same thing, just 2 M upon 2 M. Yeah, that happens. Okay, actually, like, what's this? 2M squared upon 2M, which is just M. So M times of, well, this guy, which happens to be V. So mv is the momentum that was transferred, which means that this guy is now moving with v after the collision, and this was moving with 0. And this happens all the time, that whenever you have two particles, one is moving with some speed, other is at rest, it collides, this guy gains complete energy. Or even if this is not at rest, what happens that u1 and u2, they get switched up, right? So that energy conservation, that works out, momentum conservation works out. And yeah, of course, that just means it's actually elastic collision. Okay, so it just B. Next question, body of mass m moving with speed v collides head on elastic with another body of mass 2m, which is at rest. Ratio of kinetic energy of colliding, wait, it's just elastically, right? Okay. Ratio of kinetic energy of colliding body before and after collision will be, so colliding body. Fine, fine, fine. What's the momentum? It's just like 2m1, m2, it will be 4 over there upon 3, I think. Yeah, just 4 upon 3 m times v. That's the momentum. So the negative of that is actually in this direction, right? That divide that by mass m. So what was the thing? Just 4/3 mv divide negative 4/3 mv. So now I just have v minus 4/3 v, right? If I, yeah, okay. Because I just 2m times m, and well, yeah, this works out, of course. So it's negative 1/3 v, which means that it's v squared changed by how much? It's like 1/9, right? Okay, the ratio of kinetic of the colliding body before and after collision, 9:1. So D is correct. Next question, a ball hits the floor and rebounds after an elastic collision. In this case, the momentum of the ball just after the collision is the same as that just before the collision. So it just bounces back, right? But it's less inelastic. Okay, hits the floor, rebounds after an elastic collision. So its kinetic energy is not conserved. Its momentum, well, okay, I mean, there's only one part. Yeah, there's external forces. So you can just, okay, fine. Momentum of the ball just after the collision is the same as that just before the collision. I doubt that. The mechanical, and it bounces, oh, it rebounds. I mean, of course, momentum changes direction because it's vector. Kinetic energy to the ball remains same in the collision. Well, no, its kinetic energy changes because, yeah, inelastic collision. And like p square upon 2m, so the kinetic energy imparted on Earth, that's negligible, right? I mean, that's zero basically because m is very, very, very big. So you don't have to factor that in. It's just basically this ball. So for elastic collisions, what would happen is that essentially it just goes down with v, it goes up with v after elastic collision. And the Earth, it moves with a very small speed, and its kinetic energy is negligible in comparison to the kinetic energy of this ball because p square upon 2m, and p is the same for both of these guys. Anyway, what about we talking about? Right. In this case, the mechanical energy of the ball remains the same in the collision. Mechanical energy, no, it changes. Kinetic energy changes, right? The total momentum of the ball in Earth is conserved. Yes, that's right. The total energy of the ball in Earth is conserved. No, inelastic, right? So what do you want? Oh, just want C in that case. Fine. Next question. Sphere of mass m moving with constant velocity u hits another stationary sphere of the same mass. If E is a question of resolution, then the ratio of velocities of the two spheres after collision will be, okay, sphere of mass m moving with constant velocity u hits another stationary sphere of the same mass. All right. if E is a substitution ratio of the velocities of the two spheres after the collision. Come on, that is, yeah, I mean, we can definitely do it. So this is like moving with V. It was V, right? Oh, U. Okay, fine. And this guy's stationary, and both of these guys have the same mass, I think. Right. So let's just say that after collision, this is now moving with V, this is moving with U minus V over there because momentum. So what that, yeah, my momentum decision follows. Yeah, of course. So then you just want equal to restitution stuff over there. So this subtraction is the thing. Of course, just get, well, think about it. Is this going over here or over here? Okay, it has to be going faster than this guy. That is, which is what? Just 2v minus u, right? So 2v minus u is the velocity of separation. That is upon u, that's the velocity of approach. That's equal to e, which means 2v minus u is equal to eu. Oh god, eu. Fine. So u is just 2v upon. Wait, we don't want. Oh, what is this thing? Okay, we don't want u. We want v, right? So v is just what? V is u times e plus 1 upon 2. So what do you want, by the way? Oh, okay, the ratio of the velocity of the two spheres for the collision is just, v upon u minus v. But now that you know what v is in terms of u, just basically what? It's e plus 1, well, upon to cancel anyway, just 2 minus of e plus 1, which is 1 plus e upon 1 minus e. Next question. A ball is dropped from the height of 1 meter. If quotient resistance between the surface and the ball is 0.6, the ball rebounds to a height of. So once again, the same thing, like momentum transfer to the earth is, right, okay, p square or p upon m, I think I should say. Yeah, well, that quantity is just 0, approximately, anyway, right? Okay, so ball is dropped from height 1 meter. Quotient resistance between the surface and the ball is 0.6, which means the bond rebounds. Okay, fine. So its kinetic energy is changed. Its velocity is now changed by how much? It's just 0.6 times whatever it was before. So its kinetic energy is now 0.36 times whatever it was before. So the total energy is just that, right? So 0.36 meters, that's where it's going to go back to. And that was easy. Okay, a smooth ball of mass m strikes a horizontal surface with velocity v in the direction of the angle 30 degrees with the normal to the surface as shown in the figure. If the quotient resistance for the collision between the ball and the surface is E and the ball was in contact with the surface for a small time delta t. So, okay, squished and then it goes up or something. The average force acting on the ball during the collision. Wait, what happened to it after the... Okay. Huh. Oh, so you want in terms of... okay, fine, fine, fine. Got it. So is there friction or what? Okay, smooth ball, so there's no friction. Fine. Okay, fine, it's doable. So first of all, like the component just v cosine of 30 degrees, it is that. So it passes back, of course, just e times of this guy. So what do you want? The momentum, right? Just e plus 1 times this guy. So just m v cosine 30 degree times e plus 1. Oops, what am I writing? And this is the momentum change upon time required. That was easy. So this thing is just square root 3 upon 2. Yeah. Which means B is the thing. Next question. The neutron traveling with velocity v kinetic energy E collides elastically head-on with the nucleus of an atom of mass m, mass number A at rest. Okay, neutron traveling with velocity v kinetic energy E collides elastically head-on with the elastically. That's awesome. Okay, fine. The fraction of total energy retained by the neutron is. Oh, okay, understood. Once again, just elastic. So, hey, wait a second. It's a neutron. Okay, that actually gives us, they give us the masses. Fine. So it's a neutron. It has mass 1 is, and this guy has atomic number A, so just has mass A times whatever neutron has. Right, that makes sense. So our, yeah. What's the thing, of course? The momentum is just what? Let's just say the mass of the neutron is m, then this just becomes, well, you got 2 times of m times am, which is, okay, just got 2 am, that I'm gonna cancel anyway, just a plus 1 over there, right? Distance of v. So if it was moving with v velocity, then this is the thing. So that means that this thing upon am, well, yeah. So 2v upon a plus 1, that's the velocity of our, yeah, we don't actually want it, just want the velocity of neutron, right? So for the neutron guy, it's just v times of 1 minus 2a upon a plus 1 because, well, yeah, cancels. Sure. Just v times of what is this thing? Just 1 minus a upon 1 plus a. Right. That's the new velocity that it has, which means this guy's squared. Fine. A minus 1 upon a plus 1 squared. That's the thing. That's the fractional protokinetic retained by neutron. Next question. Block of mass m moving velocity v collides with another block of mass 2m at rest. The lighter block comes to rest after the collision. The Collision resolution for the collision is mass m moving velocity v collides with another block of 2m. The lighter block comes to rest after a collision. Fine, fine, fine. The Gaussian resolution for the collision. It's elastic, right? Okay, got it. So when it comes to rest, what's the momentum transferred by? By the way, just m times v, and this guy's 2m, so it's just moving it v upon 2 now because momentum exertion. So what you have is just half. Wait, wait. If it comes to rest, it just tells us what this guy's velocity is, but that would mean our energy conservation. Does that actually work? P square upon 2m and wait. Ladder block comes to rest of equation. Hey, but initially this guy was rest, right? Yeah, this guy was at rest, and oh, it's not elastic. It's not elastic. Okay, that explains it. Fine, fine, fine. So yeah, it's doable. So just v upon two. So the question of it's just 1 upon 2, of course. Next question. I really thought it was elastic, but it's not. A body of mass 1 kg makes elastic collision with another body at rest, continue to move in the original direction, but with 1/4 initial velocity. Okay, the mass of the second body with which it collides is elastic collision is again the same stuff. So, well, yeah, let's just say it's m kgs. Then what do you have? You just have, well, that's m times of 1 upon m plus 1, right? So it's 2m upon m plus 1 times v. It moves with v, right? Okay, so that's our momentum. And now this momentum upon this guy just 1 kg. This thing is the velocity change. And you just want what? V minus this guy. Right? So just 1 minus 2m upon m plus 1. This is a fraction, which is how much, by the way? 1/4? Fine. So this just becomes, oh, it's cancel. 1 plus m is equal to 1/4. So, add these guys or to subtract, who cares? You just got 4 minus 1 upon 4 plus 1, that's equal to this guy minus this guy, which is 2m upon this guy plus this guy is 2. So m is equal to 3 upon 5. So yeah, that's the, which is just 0.6 kgs. Next question, ball moving with speed something collides analytical stationary balls is that after the collision, the direction of each ball makes an angle with the original line of motion. Find the speed of the two balls after collision. If kind of okay, wait, what? Speed is given. Find analytical stationary balls is that after the collision, the direction of each ball makes angle with the original line of motion. This is one ball, this is other ball, and they collide such that, and this guy's moving with speed 9 meter per second. Identical stationary ball, they have the same mass, fine. After the collision, the direction of the two, okay, of each ball makes angle 30 degree with the original line of motion. Hmm. Right, for each ball, right? Oh, okay, understood. So we know that it's just supposed to go with, well, yeah. But doesn't that mean it's supposed to go in, oh, this is weird. But, okay, it just collides. They never said it's actually elastic, right? Fine. Find the speeds of the two balls of a collision. Is kind of concerned in this, I don't think so, but let's just figure it out. So, of course, we know that whatever momentum you have, wait, is there friction? We don't know. Okay, we don't know about that. There might not be friction. Who knows? Original line of motion. So the line of motion is, oh, you mean in this direction, right? This initial velocity, I think. Okay, fine. Well, then they just go in what direction? 30 degree, right? With this guy. Okay, and then 30 degree over here. Got it. So what are we talking about? They didn't actually give us the velocities, right? Okay, cool. Um, let's just say their velocity does the velocity is this thing v1 and v2. So that just means v2 cosine of this guy. Fine, just for 3 upon 2 v2 and the square for 3 upon 2 v1. Well, the sum that should be equal to 9. Awesome. Or you could also say that the horizontal component is v2, horizontal component is v1. So then this vertical component would just be, it's like what? I mean, it's tan of that. I just want to square 3v1 and v2. Okay, fine. So what does that actually mean? This means that v1 plus v2 is equal to 9. And yeah, these should actually be equal, right? Exactly. Just, hey, that just means v1 is, oh, oh yeah. Oh yeah, of course. I mean, okay, that's one thing. And then they're moving with this. Wait a second. So really, that was the thing. But then by momentum conservation in this direction, so in the y direction, you can say that v1 actually has to be equal to v2, which is weird. But hey, that's what happens. So fine, just v1 equal to v2, which means that both of them are say 4.5. So what actually happens is that this guy is now moving at 4.5 in this direction, and 4.5 sort of 3, or upon sort of 3, sorry, in this direction. And then this guy is actually moving with 4.5 upon sort of 3 in this direction. You get the thing, whatever. So what do you want? The mass of the second body with which it could wait, no, that's not what we want. Which question was this? Oh yeah, this one, 10th one. Fine. Find the speeds of the two balls after the collision. Okay. Speeds of the two balls after the collision. I mean, we got the thing, right? Oh, so you want as in fine. Just 4.5. You got what's square root of 1 plus 1 upon 3, just this was like 4 to just 9 upon square root of 3. Of course, which is 3 square root of 3. I think this should work out. This should work out, right? It better work out. It doesn't actually work out. Uh, yes, that has to work out. Because there's just one over there. Yes, definitely. So 9 upon square root of 3, that's this guy. Huh. I mean, fine. So what do you have? 3 square root of 3, that's the speed. And is the kind of energy conserved? Well, initially it was what? So just 9 squared, half m, you know the thing. And versus now just have this thing squared, like 27 plus 27, isn't that right? So 2 times of 27 and 3 times of 27, different things. So now, and this one is just 3 square root of 3, which means it's B. Next question, two particles having position vectors, okay, moving with velocities is, okay. They collide after 2 seconds, the value of A is fine. Say collide after 2 seconds. Oh, they give us the position vectors and the velocities. Fine, just figure out with respect to the first guy, how is the second guy moving, right? Yeah. So the position vector of the second guy is first guy is just 3 comma 5. This one is negative 5 comma, okay, whatever. It's negative 8 comma, okay, just negative 8 once again. And that's our r vector. And what's our v vector now? V vector is just once again difference, which is a minus 4 and just 4 again, fine. Okay. So with this, because this guy just over here and then yeah, it's moving in this direction. So what do you want, by the way? If they collide, which means that it's actually you know moves over here, right? After 2 seconds, that makes sense because 2 times of this guy is that, right? Yeah. So this plus 2 times of v vector, that is equal to 0 in this coordinate. Same stuff goes for this coordinate. So this must be equal to 4. That means A has to be equal to 8. Next question, exercise 9. Show that the fractional loss of kinetic energy of an incident neutron is in head-on collision with an atomic nucleus. Initially at rest is this thing where A is the mass number of the. Wait, we just did that, right? Head-on collision. Okay, fractional loss in kinetic energy of an incident neutron with an atomic nucleus. Yeah, we actually did that. We did that, and so that was with other sides elastic. Over here as well as elastic, I think. Show that the fraction. Okay, we want the loss, right? Not how much of fraction it is now. So we already know that the kinetic energy is just this thing, it's this much of what it initially was, which means that 1 minus this guy is how much was lost, which yes happens to be this guy 4 upon 8 plus 1 squared. Next question. Shell flying but with the velocity u bursts into 3 identical fragments so that the kinetic energy of the system increases by k times. Show that the maximum velocity of one of the fragments can attain this value. Okay, fine. So this just it has velocity u vector, it bursts into three identical fragments. That's important, right? It's identical fragments. Fine. And the kinetic system is increased by k times. Show that the maximum velocity that one of these fragments can attain is this thing. Okay, well, what we can do is always like, right. So we could always add momentums to these guys and then deviate them from the mean, which happens to be u vector. And you already know that how. Okay, wait a second. Is that a good thing to be doing though? Maybe it's not. Hmm. So the energy change that you gave us, right? Energy change by k times. It's like three different fragments. It's a weird equation going on, but I'm gonna try it anyway. So let's just say that the vectors, so the new velocity vectors are just u1, u2, u3, or like v1, v2, v3 vectors. So there's some that has to be, so like, yeah, just equal to 3m times this guy, right? I guess, yeah. Of course. 3m times, so just equal to 3u vector. Cool. Well, so you'll know that the energy change was how much? It's just k times. So yeah, just v1 squared plus v2 squared plus v3 squared. That's equal to ku squared, or like 3ku squared plus mv squared, right? Yeah, just 3ku squared. That's awesome. Now what? Maybe just try to square this thing and then see if something happens. Yeah, you could. But then what about those dot product terms, like 2v1 vector dot 2 dot v2 vector or something like that, right? That's kind of a complicated thing. This is getting weird. You just k times this guy, right? Okay, fine. Or you could also say that v vector is equal to u vector plus u, okay, v dash 1 vector or something like that. That would definitely make this easier. Maybe we should be doing that, who knows. So what we'll just say that actually what happens is that v1 vector, you can write this as u vector plus u1 vector. Fine. Just gonna use this thing. So this equation just becomes this thing, u1 vector plus u2 vector plus u3 vector equal to 0. Sum is 0 for these vectors. And what about this guy? Well, just kind of, instead of u1 vector, just, yeah, square this guy. Just got u squared plus u1 squared plus that thing. And you got 2u vector dot u1 vector. But you know the thing that when you collect the u vector and then you have u1 vector plus u2 vector plus u3 vector, that's going to be 0 anyway. So what basically that gives us is that, just got 3. Okay, fine. 3 times of k minus 1 u squared, that's equal to u1 squared plus u2 squared plus u3 squared. Okay, that's much better than this, right? Yeah. But now what? What we have to prove is, so that maximum velocity that one of the fragments can attain is given by this thing. Oh, so we have to maximize this. That's kind of a weird thing. Uh, hmm. I have an idea. So you can actually break this into 9 components, because every vector is made up of 3 components x, y, z, right? So just say u1x plus u1, so u2x plus u. Okay, fine. That's equal to 0, and then similarly all this. Lagrange multiplier method. I know, but I don't want to use that because that's not good. I don't really want to use that. Uh, but I guess there's no other choice, right? Exactly. So we will use that in fact. So first of all, here's what I'm going to do. I'm going to write u1 vector as x1, y1, z1, right? And similarly for u2 vector and u3 vector. So what basically that gives us is that summation of xi is equal to 0, summation of yi is equal to 0, summation of zi is equal to 0. These are our constraints basically. So you can just say that alpha times summation of xi, that's, yeah, one of the things. Fine, and to maximize is this function, which is just summation of xi squared plus summation of yi squared plus summation of zi squared. So you could just maximize these guys individually, right? Yeah, I mean, who cares? So what that basically means is, oh, and of course, what are the thing? Maximum also is one of the fragments can attain. That's slightly different than that. Okay, this might be the best thing that you can actually have. Huh, fine. So we'll just assume that u is in the x direction, right? And then this can also be done in the same way. Wow, this got very different very quickly, didn't it? Anyway, still the same method, Lagrange multiplier method, right? So you have this thing going on. Now, just the thing is like summation of xi, well, that just becomes 3u vector. That's it. That's the only difference over here. Okay, instead of u vector, I should say u. Okay, cool. So then we can actually maximize these guys individually, right? Yeah, exactly. So then how do you maximize this guy? The sum is just 3u. Then we know that this guy is just bigger than or equal to. Hey, do you want to minimize or maximize? Wait, what do you want to actually maximize though? Oh, this is another constraint. It's not. Okay. So this thing is equal to 3k. This is another constraint. It's not something that we want to maximize. What we want to maximize is, yeah, just just this thing, x1 squared plus y1 squared plus z1 squared. Exactly. So we'll just think of this thing as a function of all of these 9 different things, and then you have these constraints going on, right? Awesome. So first we just do minus alpha times this summation of, okay, all of this stuff, summation of xi squared plus summation of yi squared plus summation of zi squared. Oh, this is just very weird. Minus 3ku squared. Oh, I don't think it's going to go well. It's just already getting complicated, isn't it? I know. I mean, I have done this method. I've done this 1,000 times. I know that this basically attains maximum when you have two of these guys moving in the opposite direction, this guy moving in this direction. But then I don't want to derive all that. Really, I just don't want to derive all that once again. I wish there was some better way to do this thing. Some more geometric way, maybe. So you could always do this, that your three particles, they move in, so two of these guys move in these directions, and then the third one has to move wherever the resultant vector lies, right? Because momentum conservation. So, or the opposite to wherever the resultant vector lies. And yeah, so then how do you get the maximum velocity? Because you have another restriction that this should be happening. So if there was not this restriction, you would just say that, yeah, fine. It's kind of a complicated thing. Okay, fine. What can we do? Can we do? Of course, just have to align them in this direction. Fine. Oh, okay. I think I know what we should be doing. So, okay, that might not actually work. I mean, clearly you have to minimize these directions because this guy is actually not having any component in that direction. So you have to minimize these things so that you have more energy to spend on this particular direction. And then you just have to make these two complete in this direction so that, you know, right. And you just have to have this at the maximum values, which means that both of these should be opposite to this, such that, you know, momentum, right? Okay, that's not what I want. I don't want to prove this really, but fine, that's one thing you could do. Okay, or you could just do Lagrange multiplier, which is maybe not such a good thing, but who knows? Let's give it a try. Okay, minus alpha times this constraint, and then you have this constraint, lambda. Let's say this thing is lambda, this will be alpha. That's alpha times this thing, summation of xi minus 3u, and you just have minus beta summation of yi and minus gamma summation of z. Okay, so let's differentiate this with respect to yi or zi and see what happens. So first we'll just do y1. If I differentiate this y1, what do I get? Just get like 2. Or you know what? For something even more simple, let's go with just y2, right? So differentiating this, all you basically get is like this is not a function of that guy. What about this guy? Just have minus lambda, then this stuff, not matter. Okay, this is a matter, this is a matter, this does matter to me. 2y2, just, this is 2y2 of course. Yeah, and minus this is not mattering because it's just constant. This is y. Then you got minus beta, that's equal to 0, which means all of the y2 values have to be the same. They in fact have to be the same as just beta upon 2 lambda, right? Negative, but whatever. Yes. Oh, okay. That's kind of a weird thing because this is not okay. Fine. This is for y2 as well as y3. But then using the same thing, you can also say like this is for z2 and z3. Awesome. So all these have the same values, right? Which basically means okay. What we just proved is this is getting weird, isn't it? Okay. So these fine. All these values actually have to be equal to the same stuff, which is just negative beta upon 2 lambda, or okay, in this particular case, negative gamma upon 2 lambda, right? Right, so this is equal to negative beta upon 2 lambda, but this is equal to negative gamma upon 2 lambda. And this is also the same thing. So Z1, Z3, well, these are equal, Z2, Z, Y1, Y2, Y3 are also equal. Okay, and then what? I mean, you could always think of just playing the motion because we don't really need three components. But whatever, we are already done almost. Okay, let's just refresh this to x1, y1, and z1, and let's see what happens. So let's do x1 first of all. Let's get what? 2x1 minus, doesn't matter. It's minus 2 lambda x1. Okay, this guy. So minus alpha, and these two values equal to 0. This should happen, which means x1 is just equal to alpha upon 2 times of lambda plus 1, right? And also let's try it out with x2. Oh, it's still going to be the same thing. Oh, that's awesome. So it's not just for this, it's also like, oh, okay, so x2 is equal to negative alpha upon 2 lambda, and then, yeah, okay, that happens. And x3 is also equal to that same stuff. Okay, so you have this thing, x1 equal to this thing, x2 equal to that equal, yeah, fine. So what should happen is that, of course, one of either alpha equal to 0, and if alpha equal to 0, then x1 is also 0, which makes no sense. Or you have this thing that 1 upon, well, there are two kinds of anyway, just 1 upon lambda plus 1, that has to be equal to 2 upon lambda, which means 2 lambda plus 2 is equal to lambda, so lambda is equal to negative 2, right? That should happen, which would mean that x1 is just equal to what? Like you have alpha upon, well, 2 times of this stuff, which is negative alpha upon 2. Momentum is, I mean, that happens anyway. And then x2 would be what? X2 was just 1 upon lambda, I mean, proportional to this guy, alpha upon lambda, right? Oh, yeah. Which, yeah, just negative alpha upon 4, right? Yeah, it happens. So, what you basically got is, right, the x values, so those are completely negative, so it just has to be like this in the x direction only. And what about y1, y2, y3? We'll see that. Also, with respect to y1, when you differentiate this thing, you get what? Pretty much the same thing, right? Yeah. So once again, you'll get the same thing, but just instead of having alpha, you'll have beta. So just beta upon lambda plus 1. That's what y1 will be because the same thing happens. Like this term doesn't really matter, right? And you know that y2 was already just, where that go? Negative beta upon 2 lambda, right? So once again, either beta can be 0 or because lambda is equal to negative 2 anyway, this works out. Well, yeah. Wait a second. It's kind of a weird thing actually. Oh, also you have this extra restriction that so lambda equal to negative 2. That means oh this is weird. Okay, so y2 plus y3 is n plus y1 equal to 0. That's satisfying that, which was to be expected. Okay, but still we've not actually figured out anything nice. Uh, anything else that you have over there? Oh, of course, this thing, right? Oh, so you can do the same stuff throughout. We will have this going on. Okay, it's getting slightly more complicated now. Let's resume. So this equation works out anyway, right? That constraint works out. Then what's remaining is basically just this equation, right? This constraint should work out exactly, which would require alpha, beta, and gamma, which we don't know because quite literally it doesn't matter what those are. Oh, oh yeah, but we did get some important stuff. that, right, that these two vectors, the vectors of 2 and 3, the second and third particles, those are the same. Yeah, because their y values were the same and their x values were the same, and also this vector was opposite to it. That is enough to conclude what I was saying was the case, right? Yeah, so through this method we just proved this must happen. And now let's just derive some nice stuff. Okay, this was way too detailed than what it should have been, but who cares? Right. So it increased by k times, so that the maximum velocity that one of the fragments can attain is this thing. Piece of cake. This guy just moving in this direction. Just it's like u over there. Oh, so u was already given to us. It has velocity u, and then it bursts into three identical fragments. Of course. So we just have this thing going on. Think about it. Just say this has velocity v, this has velocity v. This would just have velocity u minus 2v basically, right? Or u plus 2v. Okay, yeah, u plus 2v. Right. So what do you have? The energy that is v squared plus v squared plus u plus 2v squared, or proportional to this guy. Now that's just k times of what it was initially, just 3k u squared now. Awesome. So you can get what v squared should be in this way, right? Yeah, just solve that equation, you'll get a thing. Awesome. Wait, what do you actually want? The maximum velocity that, right. So maximum velocity will just be u plus 2v. That's what I'm guessing. Solve this thing. So just have 2v squared plus u squared plus 4v squared plus 4uv. That is equal to 3ku squared, which means 6v squared plus u squared is 4uv plus 3k minus 1. So 0. And that's different already. For some reason they have 2 times of k minus 1, which is not what I wrote. We'll see, maybe something will happen. So what do you have? V is equal to minus b, negative 4 plus minus square root of b squared, which is a 16, plus 4ac. Well, that 2 cancels anyway, just this one's 2 square root of, so this thing squared, but then it falls out. It's 4 minus 4ac, just got minus 6 times of 3k minus 1, it seems. And all of that, well, yeah, it's a c over there, right? Exactly. Upon 6. Okay, 2 times of that, of course. So what does it become? It just becomes negative 2 plus or minus, what is this? Square root of 4 minus 18k plus 6. And that's different already. Yeah, it has 10 minus 18k for some reason. Did I mess up somewhere? Most likely I did. But where? This was just 3k minus 1, right? Yeah. 4uv right there. Just got u squared plus. Oh, this should have really worked out. For some reason, it's not working out. It just splits into fragments, and then this is what's happening. And just 4v squared, just 6v squared plus 4uv plus that is, oh shit, it's 1 minus 3k over there. 1 minus 3k. Huh. Yeah. So just have plus 6. Got it. Plus 6. That is still not working because it's got 18k minus 2 now. Oh. That is going to go so well. Okay, so just b squared minus 4ac and 16. So that 4 just comes out just 2 over there. 4. Then that 4 comes out just minus 4 times of c, which is, yes, it's just this thing, just 18k minus 6, and it happens to be 18k minus 2. So this should be 18k minus 2. That's definitely not what this thing is. Increases by k. I mean, initially it was that, right? Wait, by increases, what do they mean? Does it become k times of what it previously was, or does it become like k plus 1 times what it previously was? What if it was k plus 1? So if we replace k by k plus 1, you have 18k plus 2. That still doesn't actually make sense. It's just that bad as well. Okay, that's not going good. K minus 2. No, doesn't work. You have 2 times of k minus 1. which I don't know how they got. Something is going wrong, right? Yeah. We got v plus 2. Yes, just u plus 2v. That's guy squared. V squared plus v squared plus. Okay. Okay. Energy, right? Just get after this guy. 3k u squared because initially it was just 3 u squared. So like it. Okay, I think we should stop at this point because and maybe just wrong. Who knows? So we'll just stop here. I'll see you guys in the next video because it's very late in the night. Yes. Bye.